Hi everyone, my name is Shmuel Berman, and today I'm going to be talking a little bit about intra-update sniping vulnerabilities in smart contracts, which are vulnerabilities that arise when we update smart contracts and smart contract systems. Before we get into that, we have to get into what smart contracts are. In order to do that, we have to get into a little bit of background about blockchain. Blockchain, as some of you are aware, some of you have heard of, is this kind of trustless system through which we have many network participants, and they ensure that everyone's being honest, that everyone can only spend their money once, that everyone can transact with each other without a central authority to dictate how those transactions and when those transactions take place. The important thing here for our discussion is that the blockchain takes place in the form of blocks, meaning it's a chain of blocks that occur every so often. And at these points that are called blocks, the blockchain updates and a transaction can take place. If you transact in between blocks, we wait until the next block to actually push that to the ledger. So then those are just basic transactions, just transacting money, Ether, Bitcoin, whatever you want to call it. Now we get into more complex things like smart contracts. What is a smart contract? It is some code that is run in the same trustless-based system using a lot of complicated math that looks a little bit something like what's on screen here. It has variables, methods, like any typical code, and it runs code. Many users run it millions of different times to verify everyone has the same result. And this code actually has consequences. You can spend money with this code. You can perform functions with this code. And this code, importantly, this logic can't be changed. Right? This is immutable. Once it's been on the contract, once it's gotten on the blockchain, you cannot take it off. You can inactivate it if it has no more money. It won't do anything, but it's on the blockchain forever. The logic, at least. So the next thing we're going to establish is if you can't upgrade the logic, like we saw in this case, this is on forever, then what do you mean upgradable smart contracts? Well, there's a small loophole we can use to get around that because we can store variables. As you saw on the previous slide, we can change those variables. This string is a message which can change. We can change it to be whatever we want. Well, in the same way, we can actually have these addresses because every single smart contract has an address, and we can delegate logic, like methods, to different contracts. So a user can interact with a proxy contract, and then the logic behind that contract will be delegated to a different contract, and we can have a function inside the proxy contract which will allow us to change the address. So if we change the address, the logic is then delegated to a different smart contract. Fine. So here's a little diagram. The users interact directly with the proxy, and then through the proxy, the only functionality there is to let us change the implementation contract, and we can make new implementation contracts as we wish. The users will not feel it because the proxy contract is the one that they will be interacting with, and that never changes. That we can't change. Nor can we change the implementations, but we use this loophole to get around that. So now that we understand what these systems are, let's get into a little vulnerability that can arise. We talked before about block times, meaning updates, including pushing a new contract address, can only be pushed at every block, which can be 13 seconds, it can be 10 minutes, depends on the exact chain. In this system, we have two proxy contracts and two functions, and they're both unsecured, unauthenticated, which is normal, right? Anyone can see someone's wallet balance. That seems pretty normal. We want to update that to a different system where the account owner can withdraw funds. So we're making two separate upgrades. We're changing both of these proxy, both the authenticator proxy and the function proxy, to be to different contracts. We're changing those. We're pushing both of them to the blockchain. The problem is that now that we've pushed those to the blockchain at the same time, we have no idea which one is going to update first. Either the proxy authenticator or the proxy function can update first. So we see that if the proxy pointer to the function updates first, then anyone can withdraw funds, because the second function, if you recall here, is to withdraw funds, and that's a vulnerability. And the way we solve this is to model our system as a configuration file and analyze the security levels. And if you want to find more about that, please feel free to ask me questions. We'll go over it very briefly right now. We're going to look at this as a graph and draw every single upgrade state that exists inside of this graph, how it can upgrade. And we're going to analyze, is the security level of every single every single node in that graph the same or identical, or at least as high as it is in both the initial and target state. we're only going to test for the intermediate states. We assume the initial and target states are secure. So I think that's an important vulnerability that arises as smart contract systems get larger, and we have to acknowledge that they do have vulnerabilities when we update them.